This video covers spin-orbit coupling, or SOC, in quantum mechanics, looking at its relativistic roots and consequences in molecular photophysics. SOC mixes pure non-relativistic states, leading to new conserved quantities and macroscopic consequences like phosphorescence and fine structure. SOC is the relativistic interaction between an electron's spin and its orbital motion. This single operator acts as a, quote, kingmaker in molecular photophysics by mixing states of different multiplicity. Its consequences include fine structure, intercombination lines, intersystem crossing, and phosphorescence. The phenomenon of SOC is purely relativistic, originating from the Dirac equation. It is absent in the non-relativistic Schrödinger-Hamiltonian. SOC only emerges when the Dirac equation is reduced to a low-energy effective Hamiltonian, such as the Pauli or Bride-Pauli Hamiltonian. The structural core of spin-orbit coupling is the L.S operator. The prefactor includes the Thomas precession correction, which is necessary for a rigorous relativistic origin. The operator form dictates that SOC is diagonal in the total angular momentum, J, not L or S separately. The presence of SOC means that L and S are generally no longer separately conserved. The total angular momentum, J equals L plus S, becomes the conserved quantity. The eigenvalue of the L.S operator is explicitly defined in the total angular momentum basis. Spin-orbit coupling is responsible for resolving the fine structure of atomic spectra. In both hydrogen and alkali spectra, SOC and other relativistic terms cause splittings in energy levels, moving beyond the gross structure defined by central field and electrostatics. The Landé interval rule describes the exact spacing of reorganized energy levels due to SOC. The rule, EJ equals AJ, is a direct consequence of angular momentum algebra. SOC reorganizes each term into multiple J-resolved levels, altering the electronic spectrum. As the atomic number increases, the standard LS coupling regime degrades. For light atoms, LS coupling dominates. As atoms become heavier, the increased SOC leads to JJ coupling, where the, quote, good quantum numbers themselves change, indicating a fundamental electronic property change. SOC breaks the clean factorization of electronic states, allowing strictly forbidden intercombination lines to appear. Non-relativistic rules forbid these transitions because the electric dipole operator does not act on spin. SOC introduces state admixtures, giving intensity to these otherwise forbidden lines. Transitioning to molecules destroys the spherical symmetry present in atoms and quenches orbital angular momentum. Modern molecular theory must treat SOC as state-to-state coupling, calculating matrix elements of the Bride-Pauli operator between multi-electronic states. Spin-orbit coupling is the, quote, kingmaker for molecular photophysics. It enables intersystem crossing between singlet and triplet manifolds, which is formally forbidden in non-relativistic theory. By mixing singlet character into triplets, SOC allows for phosphorescence to occur. The heavy atom effect is a, quote, blunt instrument of molecular design. Adding heavier atoms significantly increases SOC, accelerating singlet-triplet mixing. This makes intersystem crossing and phosphorescence much stronger in heavy atom systems, compared to slow phosphorescence in light organic molecules. El-Sayed's rule shows that changes in orbital character can enhance SOC. The rule states that effective SOC is enhanced when there is a change in orbital angular momentum character between the two states. This explains fast intersystem crossing in molecules like benzophenone, even without heavy metals. Advanced dynamics show that spin and nuclear motion cannot be cleanly separated. The spin-vibronic mechanism means that non-adiabatic coupling and SOC act together. This coupling is critical for ultra-fast excited state dynamics, like intersystem crossing, and for modeling optical spectraline shapes. Spin-orbit coupling does more than correct energies. It fundamentally changes the nature of the states. It alters the symmetry structure of the Hamiltonian, downgrading separately conserved quantities. This affects spectroscopies, absorption, emission, and opens new pathways in photochemistry.